Hello, everyone. Thanks for joining. Really excited to be here and talk about CRDTs. It's still a trendy topic in the industry nowadays. So first of all, a short disclaimer. I don't claim myself to be like hardcore academia guy or a distributed systems expert. I'd rather want to show you that some recent academia achievements actually can bring a lot of value and can help to solve real-world problems. So I work at TomTom in Amsterdam on a project called NavCloud, which is a cloud-based service for storing and seamlessly synchronizing personal data of our users. Navigational data, but not limited to that. And of course, NavCloud, as probably most of the services, aims to be available, scalable. We have to be legally compliant and secure because personal location-based data can be quite sensitive, of course. And developers in NavCloud projects are full-stack developers, so we hack on backend services, on client libraries and SDKs, and also on infrastructure. So this really helps us to understand how developers that integrate with our platform experience our product, our platform on different layers like REST APIs, client libraries, and such. So speaking of the development stack that we're using, we're a Scala shop, at least for the backend services. And yeah, we'll do like typed functional programming. And we also leverage some open source distributed services in our platform. And for the client library side, we do have support for different platforms, mobile platforms. And these client libraries, they basically do lots of heavy lifting for our clients and for developers that integrate with us. So they handle like session management, connection state monitoring, background syncing, and etc. So I want to argue that this is the NavCloud nature, but actually it also applies to probably most of the data synchronization systems. So of course, nowadays, like users have lots of devices, personal devices, and they all are meant to be connected to the internet. But the problem is that connection can be unstable. You go to the parking garage, you lose your connection, but users expect their applications still continue working, right? And of course, we also have problems with limited bandwidth or network data plans. For example, in TomTom case, some of the devices, personal navigation devices that we ship to the market, they're equipped with built-in SIM cards. And TomTom pays for the data plan on these SIM cards. So all the data that is used on these plans is expected to be used efficiently. And again, yeah, offline readiness is really expected from the applications that build on top of this platform. And the data that is distributed across multiple devices owned by the user can be modified and modified concurrently. And these changes, they can be potentially conflicting. And our platform has to handle that. And of course, there is also no guarantee in an updates order. And our users, they don't expect us to lose their data. That would be really unfortunate. And of course, when users make some changes, whether it's offline changes or online changes, they expect that the data will converge to expected value. So how to deal with this nature? Of course, you can probably write lots of logic on the server, on the client libraries to handle the cases, especially edge cases. That's how we were also starting with NavCloud in 2013. The first data types that we were syncing, we were covering all the edge cases that can occur when you are offline, when you're back online, et cetera, et cetera. It's not that easy. And as Linus Torvalds once said, good developers, they actually try to solve their problems on the data structure level. Because data structure level, data structures, they usually provide good abstractions. And underneath, they can really help to solve the problems efficiently. So here enters CRDT. So as probably some of you know, CRDTs are a family of data types. And these data types, they have their own algebra. The R stands for replicated. So CRDTs are meant to be distributed across multiple nodes, multiple let's say, clients or multiple devices. And CRDTs, they guarantee that the data will be in conflict-free states. So CRDT itself handles conflict resolution for you. But how does it do that? The key ingredient in CRDTs is a merge operation, or in literature also called join operation. So merge operation is a binary operation on two CRDTs that yields another CRDT. And the key thing in here is that the merge has to be commutative, associative, and idempotent. So how does it help? Well, as we know, probably in distributed systems, it's really hard to guarantee the order of updates. But that's not a problem, because merge operation is commutative and associative. We can receive updates in any order. It's also infeasible to implement exact once delivery. So we have to rely on, let's say, at least once delivery. But that's not a problem for CRDTs, because merge is idempotent, actually. So what does it bring in practice? The thing is that CRDTs is not about servers and clusters usage only. Actually, when you use CRDTs also on the client sides, client libraries, let's say, you can get additional benefits, like local updates, when you just can modify your data without having any connection. But you know that later, when it gets connected and you push that data and propagate that, the data will converge to the expected state. And this is really beneficial to decouple the data modification flow from the communication flow, let's say. Let's see some examples. So the first one is gcounter. It's a grow-only counter, so it has only one operation, increment counter. Really simple. So let's say you have a website and you want to count number of hits on this website. And of course, the website has to be highly available, so you have more than one machine in the fleet. And probably the naive approach would be to just have a local counter on each machine, counting the hits. And then upon gossiping between the servers, they have to exchange the data and merge it. How do you merge the data? Well, probably we can just take two counters from two machines and then just sum them, and that's it. Unfortunately, that does not work because the addition operation is not idempotent. So if you, upon gossiping, exchange messages twice between the nodes, then you overcount. So gcounter solves that problem a little bit differently. It actually uses the map underneath. So it's a map from replica ID to the replica counter, and then each replica can increment only its own counter. And upon gossiping, when they exchange their data, actually when they merge it, they have to take the max of corresponding elements for each element in the map. And to count the sum of elements, you just need to simply take a sum of all elements, all the values in the map. Why does it work? Well, because the max function is in fact CRDT compliant, merge compliant. It's commutative, it's associative, and it's idempotent. Another example is gset, grow only set. So it's a set where you can insert new elements, you can remove. Again, so naive approach to have a single underlying set on all the machines, and then upon gossiping, just when two values have to be merged, just take a union of them, right? Will it work? Well, in fact, it will. So that's how gset works. It has just one single set underneath, and then the merge function is simply union of two values together, and the total value is just the value of the underlying set. But why does it work? Well, the union function, unlike addition function, is actually CRDT compliant. So it's commutative, associative, and idempotent. Good. So let's see how we can leverage CRDTs in our case for data synchronization in NavCloud. So one of the types of data that we synchronize is favorite locations. So let's say you drive somewhere, you like this place, you mark it as favorite location, and it gets magically distributed, replicated across all your devices and to the cloud. We also synchronize different types of other types of data like poise, tracks, etc., but that's probably the simplest one. So what could be the naive approach in that case? Well, we can just have like an array of favorite locations on the node, and then we just, while being offline, we modify it, add a new element, let's say. And then when we get the connection, we just push the data to the server and then overwrite the value on the server with last right win strategy. Unfortunately, that's not going to work. And the problem with that approach is that, again, we have unstable connections, and when the actual update time can be drastically different from the time when you send to the server, and again can be different from the time when the server receives that because of network latencies and etc. And of course, clocks are unreliable. All these problems lead to a nasty thing, which is when stale update may win. And this is definitely not what users expect. So what? Let's try CRDTs. CRDT, in fact, really nicely match the data synchronization platform nature, because we have unstable connection. That's fine, because we completely decouple the mutation of the data from the connectivity, so we can easily update the data while being offline. It's fine. Limited bandwidth. So this talk mainly about the type CRDT, which is called state-based CRDT. There are also operation-based CRDTs. So in state-based CRDTs, in the original ones at least, it's expected that the whole state is being transferred upon gossiping. And it's not really network efficient, right? So what we did, we actually extended the algebra of CRDTs with a diff operation to be able to calculate the exact amount of data that needs to be transferred over the wire to another replica. And of course, we also get via CRDTs things like offline addition and then concurrent changes with potential conflicts are also handled. Ordering is not guaranteed. It's fine because we have merges idempotent. We don't lose any data because we always merge. We never override. And then the data convergence to expected value. Will it work? So in fact, yes, it will, because we have the same data everywhere, on the servers, on the clients, and even in our data store. Data store. OK, so we actually use the RIAC from Basha, which is masterless distributed key value store, inspired by Amazon Dynamo paper. So it has different approaches for conflict resolution. One is last right wins, which probably not something that you want to use. Another one is based on siblings. So siblings are conflicted values that are created when you write back to the database a stale value. And in that case, it's the client responsibility, your responsibility, to solve the conflict upon the next read. And sometimes it's considered to be not a little bit client-friendly, of course, but in our case, it's fine because we do store just CRDTs in the database. So for us, it's just a matter of calling the merge operations on two sibling values from the database, and that's it. Really simple. So let's have a look how we can implement a CRDT set that can allow us to seamlessly synchronize favorite locations across our devices. So what do we want? We want this set to support addition and removal operations, so gset not really work for us in that case. We want to optimize this set for mutations, and the footprint of this set should be more or less compact because of the network data restrictions. So the first one, you can have a look from you can look at the set from the literature. Is two-phase set. It does support addition and removal operations, and it's modeled. It can be modeled as two G sets: one for added elements, another one for removed elements, like tombstones. And in this example, if we want to remove an element, we simply need to take that element from the add set. Well, we still keep it there, and put that also to the remove set. How do we merge these two replicas? Well, underneath of the two-phase set, there are two G sets, and we know that G sets are mergeable. They are CRDTs. So we just need to merge corresponding G sets, and that's it. And to calculate a lookup in that case, we simply need to find all elements in the add set which are not in the remove set. It's deadly simple. Here's some code examples, but I will share later a GitHub link to this repository. Two-phase set didn't work for us because once you remove an element, it's removed forever, right? You cannot re-add that again. And the elements are immutable. Of course, one might argue that you can model the modification of an element as a sequence of delete and then add again operation. And that probably will work, but the problem with that is that it will quickly inflate the remove set. And we will see later how it can bite us. So another example of CRDT set is last right wins element set. which also supports additional removals, but this time it actually adds a timestamp to each element. And again, can be modeled as two gsets, one for added, one for removed elements. And it does support re-adding of the element. To re-add an element to the last right win set, you just need to increase the timestamp. So again, an example, each element is a pair of logical clock and a value. And again, the merge is deadly simple. We just need to merge corresponding gsets. And to calculate the lookup, we simply need to find all the elements in the add set which have the higher timestamps than their corresponding values in the add set, or in the remove set, sorry. And yeah, here are some code examples. The merge is everywhere is the same. We just take a union of gsets. It still has this problem of immutable elements, so you have to you will quickly inflate the remove set. So we looked at another one, which is OR set. OR stands for observed and removed set. And the same, it also supports additional removal operations. This time, a unique tag is associated with each element. And to re-add an element to in the OR set, you have to simply introduce that element again with the different new unique tag. That's it. Again, the merge of these two replicas is simply merging two underlying G sets. And to calculate a lookup, in that case, we need to find all elements in the add set which have unique tags which are not in the remove set. And here's some code for that. Cool. The same problem still. The elements are immutable. We will quickly inflate the remove set. So we decided that we can somehow extend the OR set with this mutation functionality, and we called it observed updated remove set, or shortly our set. Pun is intended. So each element in that case also has an identifier. This identifier is immutable, so if you want to modify an element in the set, you have to preserve this identifier. And then we have a timestamp which has to be changed every time you mutate the element. In this case, actually, we're decoupling. We have kind of identity, which is immutable based on the unique identifier, UUID, for example, and then the value, which is mutable and can be mutated. So underneath, actually, how it's implemented is implemented as a single underlying set, not G sets, just for the sake of optimization. So we use this discriminator removed Boolean flag to actually distinguish removed and non-removed elements. And then we also have a metadata like ID and timestamp. So here's again an example. Each element in replica is free of all fields, so ID, timestamp, and the value, and then the optional removed flag. So the merging here is a little bit more involved, well, only a little bit. So we actually have to take a union of two replicas, then group elements by IDs, and then in each group we need to find a winner. So how do we find a winner? Well, we have a timestamp, so we can just pick the element with the highest timestamp. Simple, right? And how do we calculate the lookup? In that case, we simply need to filter out the elements which are removed. That's it. And here's some code examples. So let's try to apply that to our favorite location API. So exactly, we model each element of our favorite location as like a state element, which has this additional metadata attached to it, plus some data. So instead of favorite, here it can be sort of any data, right, which is sort of business domain related. And one might argue, so you mentioned that we take the winner by timestamp. What happens if timestamps tie? That's a good question. So compare function and the merge function have to be deterministic. So in that case, if we have a tie in timestamps, we have to continue comparing the elements metadata and then compare the removed flag. So then we can have like an add or delete bias, for example, depending on our business logic. And then we have to compare the rest of the attributes going into like business domain-specific attributes like name, location, and etc. It's important to have compare function and merge function deterministic. So okay, now we have this CRDT for storing favorites everywhere in our application, in our server, in our database, everywhere. It's the same technique. We just merge the data that comes from another replica, And when we also modify the data, we also merge it to our local store. It's a pretty simple model to reason about, pretty simple model in unified model to code. And for example, in that case, the server is not really that much different from a client. It just gets some data from the client, and then it needs to merge it with the data that's stored in our primary data store, push it back. That's it. It's, again, pretty easy to code. So, OK, so CRDTs everywhere sounds perfect. Is there a trick or something, right? There is always a trick. So yeah, let's have a look at some considerations and limitations that we observed, at least in our use case. So I think the most common question that we get from people who learn that we use CRDTs in production is that, so how do you deal with garbage? And that's a problem, because CRDT sets tend to grow because of tombstones. So every time you delete an element, it's still stored in the underlying set as a tombstone, and it's potentially an unbounded growth. And we all know that unbounded data structure is like a killer of distributed systems, so we have to deal with that. True. So, OK, we want to prune deleted elements, but the question is when? Well, intuitively, we can think of probably all nodes that hold this element that is about to be, that has been removed, and we want to prune it. They have to observe this deleted operation, right? Otherwise, we will have an element resurrected again, which is something that we don't want. We can apply the time to leave strategy for tombstone. So after some time, we just get rid of this tombstone. The trick with that is that this time to leave strategy has to be applied independently on all the nodes, on client, on the server, and this is a really important requirement to hold. Another trick that we saw is that as I already mentioned, we extended the algebra of CRDT with diff operation, with delta operation. And the reason we do that is to optimize the bandwidth consumption. And when, for example, in that case, the client being aware of what the server has, because the client from time to time gets data from the server, it can calculate the difference from the last observed value from the server, and then it sends 2 elements to the server. But server, in our case, is not aware of the replica state of the client, of a particular client. So what does server has to respond? So it can respond the full merged set, but it's super inefficient, because we will, in that case, we transfer already 2 elements that already have been observed by the client. So we can do better by using a simple technique, really simple technique called scope diff. So instead, the server responds only with element value that has won over the value that client has sent. And in that case, it's only the modified B, and the client just simply merged that. Client doesn't need to know whether it's a scope diff or normal diff. Client always merges the value that it receives from a server. So it's really, really a pack for the client. But it's optimized still. There is another interesting case, which is the other way around. So we have this subscription mechanism where the clients can send a request to subscribe to changes from the server. And upon the first bootstrapping phase, server has to send like the latest changes from that client has not observed yet. The problem is that, as I said, server is not aware of the state of the replica of the client, and in the naive case, we can just send the all values that the server has. But again, it's really inefficient, especially if the client subscribes, then connection is dropped, then subscribe again, et cetera, et cetera. So what we did instead, we introduced some metadata, which is stored outside of CRDT. So it's a little bit of trick, which actually associated with every element in the set on the server only, which is a clock. It's just a monotonically growing clock. That is, every time an element is modified, then this clock is increased to the maximum value +1 of the clock of any element within the collection. And the server, upon any update, sends that updated data to the client with the clock value. So for the client, it's just a matter of storing that clock locally, and then upon next connection, when it wants to subscribe, it sends that clock. Based on that clock, server can calculate the elements that have been updated since the last time that the client has observed the changes. It's really efficient technique and also allows us to really reduce the data usage of the subscription channel that we have. So let's talk a little bit about time. There is a trouble with time, right? So there is no such thing as reliable time, unfortunately. I like this quote from Jonas Bonner from one of his presentations, arguing that actually when we are tracking the time, we're less interested in absolute values of time. Actually, it's more about causality. Causality and ordering of events, that's what's important. And in our case, the events is just the ordering of updates to a single element within a set. That's it. Time can be sometimes just good enough. It allows us to deterministically order the events, the updates to the same element. So, of course, we can look at that from a simpler point of view, where we have just ordering updates within a single node. In that case, the timestamp field in our metadata is just a logical clock. That's it. Absolute value is not important at all. It just should grow monotonically. So the only thing we have to do is to ensure monotonicity. So when we retrieve a timestamp from any provider which is available on our platform, mobile platform, etc., we just need to ensure that it doesn't go backwards. That's it. And sometimes it happens, like if we use like system current time millis, there's no guarantee that it doesn't go backwards, right? So at least we want to preserve that. Ordering of updates from different nodes is much more complicated, of course. And being a company that has to deal with lots of navigational devices that have GPS and GPS clocks, we might be sometimes a little bit in more fortunate position. So, of course, the GPS clocks provides really reliable time, so we can just rely on that. But lots of our clients, mobile clients, don't have that. And in that case, at least we prefer to use server time to a client's time. So, for example, whenever connection is available, we fetch the server time, cache it, and then calculate the elapsed time since that. And this provides at least more reliable time than we can have otherwise. There is still an edge case, this warning that saying that if we have multiple clients exactly at the same moment modifying the same element within a collection, we can have a problem. And the same applies when we completely have no reliable clock at all. Unfortunately, these edge cases may happen still. So we already seen that picture where on all the layers, application, server, database, everywhere we have this merge operation. One merge to rule them all. There is a trick with that, of course, that the clients and the server have to have exactly the same merge behavior, which means that given the same input, they should produce the same results. And that's crucially important because if it's not the case, if we have some rogue clients that produce different results, then they can organize these nice endless synchronization loops, which are not really funny to deal with. Yeah. So another thing that we also observed is that we already seen our structure of our set element, right? So each element has a metadata and the data associated with that. And when we compare elements and when we merge them, we actually need both metadata and the data because we always have to compare also the data if we have a tie otherwise. So we thought like, okay, can we lift some information about data to the metadata level, which will allow us to make data optional? And actually, we can because we can introduce a tag, which can be based, for example, on the hash of the value. We can introduce that to the metadata level. And in that case, we can do all the CRDT operations, merge operations, compare elements on the only metadata level and have data lazily loaded. And in that case, we can have a pretty flexible synchronization strategy where we can have an eager or lazy fetch, for example, and this is really beneficial for our clients. So sort of a summary, what have we learned? I guess the point is kind of that the academia sometimes might be not that scary to pragmatic developers, as it might seem. Of course, there is certainly a learning curve. When you first encounter CRDT and you go to the Wikipedia page, you read immediately that CRDT is like a bounded semi-lattice with a join operation, which sometimes might sound a bit cryptic. But of course, still academia and recent researchers provide really nice abstractions that can really help you to tackle with your problems in a more efficient way than just coming up with your own complex and homegrown conflict resolution logic. And I think important point also that we really need a better and simpler abstractions to develop offline radio applications. Like there are not that much applications still that are really can nicely handle the offline synchronization scenarios and offline access to the data, and etc. CRDTs do provide a great value with that. There are some caveats, as we saw. Things also like even higher order abstractions, like, for example, Last language by Chris Michael John also could be a nice answer to that problem. There is a code available on GitHub with some samples in Scala and Java for all the collections that I've shown. And yeah, thank you very much. These are my two co-authors, Nami and Didier. They're awesome. And without them, this presentation would not be possible. So thank you.
They don't. This technology stays relatively exotic. And when I looked into available libraries, both in CRDT camp and operational transformations camp, I realized why. They're very monolithic, and it seems to be nearly impossible to integrate them in an existing project or to use them with a conventional framework like Rails. But even when you think about building a project from scratch, given CRDT, where do you put the business logic layer? Because a client seems to be talking to a database abstraction layer, and we want like authentication, access control, batch operations, transactions, like triggers, comments non-related to data models. So where does that go?
Yeah, there is a problem with these kind of like platforms that provide so much abstraction. So that's why, for example, we don't use any of these. We actually came up with like our own implementation of CRDT, which is pretty slim, and it's just a collection in the end, right? It's just like you probably like when you synchronize like a bunch of data in a collection, like you have a list or whatever array, and you just convert that to CRDT. It's pretty natural in the way. Of course, I see what you mean, like higher order frameworks that really handle lots of stuff for you, and then there's really like far away, you know, from your business logic, and in the end. This is an interesting question in the end. So I think in general, the question about adoption has the sort of adoption problems have different sources. It's like one of them is that it's not all data can be modeled in terms of CRDT, so you really have to tackle that problem that you're trying to solve. And of course, the collection case is pretty nice because it's really nicely covered by CRDTs. But there are some data types that's a little bit harder to, you know, express in terms of CRDTs. But yeah, I think we need a little bit. It would be nice to have actually CRDT types be more like a slimmer, maybe part of even like a standard libraries of different languages that really do provide like simple operations like merge and diff and etc. And then you can build on top something harder, something more sophisticated. But I don't know. Does it answer your question? Or?
I have an impression that it's like a very long shot. So you are to go all the way for it, and go all custom, and build all your own stack around CRDT, like it becomes your whole backend. Or you have to go the old school way.
Old school way. Yeah. So of course, like in our example, for example, our REST API exposes CRDT compliant API, right? So when you work with that, when our clients work with that, they work with CRDT compliant API. So it's a little bit different from like traditional API. And this is also kind of a problem when you integrate with, like, you have to build up this whole stack, right, from the server to the client. That's a problem that I do acknowledge, definitely. So as I said in the beginning, we were fortunate to implement the whole stack from the server to the client libraries. So we had much more control over that. Of course, when you integrate with like a, let's say, third-party service, you don't have an option, right? Although I had some discussions at one of the previous conferences with the mobile guy. Actually, even he contributed to our Java CRDT library to make it Android compliant. And we had that discussion that can you leverage CRDT only on client side, for example, when you work with a third-party API that doesn't provide CRDT compliant API. And in fact, actually, I think it's still beneficial because you can have you have this nice abstraction that takes care of concurrency nicely, and you have local updates and everything where the programming is easier even on the client side only with that. Yeah, I think we still need to think how to bridge the gap between, like, to build the whole layer from the server to the client and back. Yeah, that's true. That's why I also mentioned things like LASP that can help with that, because basically they build up the whole protocol from the server platform to the clients. But it's still under research.
So I want to confirm, like, for the non-causally related updates, like when they're like non-causally related, you rely on the server flow timestamp clock, right?
Yeah.
To resolve the conflicts. And I want to, like, is there an edge case where like your CRDTs are compatible and convertible? What do you do in this case, or like there is no such case at all?
Incompatible in which sense?
Not resolve a conflict. Let's say like the world clock timestamp was the same.
Well, I mean, we will always resolve conflicts automatically. That's kind of like, we even wouldn't know. Yeah, so if we look at the compare function, actually, it has to be deterministic, right? So if we look at so if there is a tie with timestamps, we will compare the remove, flag, and rest attributes. We consider that if there are updates with exactly the same timestamp, for us, it does not really matter which one wins. Of course, it depends on your business model. Of course, maybe you don't want that. In that case, yeah, you have to think. Also, you can implement a little bit more sophisticated merge model, right? So you can not just pick one element. You can actually merge them. Yeah.
So the CRDT is a composite data structure. How do you translate that, or how do you decide to encode that in your data store, like in React or SQL database or something? Where did you guys end up?
Yeah, so the thing is that React itself has CRDT implementations in place, at least React 2.0, since 2.0. We didn't use that because multiple reasons. We wanted to really have full control over the logic, that how our CRDT set is implemented, and etc. So for us, it's just, as I mentioned, we leverage React conflict resolution strategy, where it always keeps all conflicting values, and then we, on the clients, or in our application code on the server, take care about merging these together, right? So I guess this with SQL database is a little bit tricky, because with SQL database, I guess they will just override that, right? So they won't create these conflicting values. So I cannot answer that question in regarding to SQL, but the databases, yeah. So if you're unfortunate to use database with last right win strategy, then you have to think about it a bit. Maybe you have to introduce some intermediate layer that will take care about this merging before pushing that to. But yeah, that's always a problem when you basically switch from this always merging strategy to like last right win strategy. There is always an edge case where you might lose some data. This is always like, this is the boundary where bad things might happen. So. Oh, yeah, yeah.
It gives you back and then tells
Absolutely.
you merge it, and
yeah.
like he won't let you override.
No.
Until you resolve the conflict.
Yeah. Yeah, that's the point. So React with this allow mult strategy is called, when upon next read, when when you read from a key which has like two conflicting values, siblings, then both siblings will be returned to you, and then you will have to merge them. That's how React works. And it wasn't designed specifically for CRDT. So in a more traditional approach, it was just your client code responsibility to merge them together with your homegrown logic for conflict resolution, etc. It doesn't have to be CRDT, necessary CRDT. It can be anything, right? But yeah, that's how React works. So it always returns you all the conflicting values. It never drops anything.
You're saying that many people they will either SQL databases because they don't have this support.
Yeah, that's the point. Yeah, yeah, with SQL database.
Something else, a log or something else that you have multiple.
Yeah.
But are you just doing like JSON stringify, and JSON parse all over the place?
Yeah, yeah, yeah. So we just serialize to JSON, and yeah, it's just like a binary data. Yeah, I mean, it can be anything, protobuf or whatever. Sure.
Are there any like limits on how large a single CRDT can get while still being useful? Like, did you encounter them, or are they?
Yeah, yeah, absolutely, absolutely. I mean, the bigger CRDT, the higher payload, network payload that has to be transferred over the wire, like between the database and the server, and etc. So we put some boundaries on that, but it's still tricky. So of course you do have to put boundaries, but the question is what to do next, right? So I mentioned this time to live strategy where you can gradually get rid of tombstones, let's say, but in cases of most of our lawful clients and the users, it's not a problem because like the problems start occurring when you have like thousands of elements in a set, which for single user is, in our case at least, it's probably unlikely. But of course, when you have like beta test users or developers that integrate with our platform, write lots of integration tests, then they can easily reach these limits. And then in the end, they can be just rejected. So our platform prefers to reject these kind of updates rather than just degraded performance. That's kind of the point. We're thinking about that. It's not. It's not that easy. So of course, yeah, you can probably do that. You will have to apply the same technique like on all the clients, right? Yeah. This has some limitations basically because the thing is that so there is no any coordination between like updates on different clients, right? So when they just like evict the elements, like you don't know which element will be like. They're not necessarily in the same state, right? Replica can diverge. And then if they start dropping these updates, it's not necessary that it will drop the same updates everywhere, right? This simply leads to like situation when like different clients will just chase each other and then just try to resurrect it all over again. So it doesn't really work. Probably it might work with like 1 or 2 clients working with the same CRDT set replica, but then with the higher distribution of clients, I think it won't work. Any other questions? Yeah.
How does CRDT compare to operational transformation?
Yeah, so I'm not really familiar with operation transformation, but from what I heard, it's more like the CRDTs that we work with is state-based CRDTs. So they are quite different from the operation-based CRDT, where an operation-based transformation is actually closer to operation-based CRDTs, where you actually, as far as I know, of course, operate with like changes over the wire, right? You don't transfer the state of the data. You sort of say, for example, add this, for example, or modify this. So it's rather operation transformation. That's why it's called also, I guess, like that. But yeah, the problem, well, I cannot say for operation transformation, but for example, operation-based CRDTs, there is a problem with the additional requirements for the network connectivity. So when basically for state-based CRDTs, the order is not important, and you can just rely on any order of updates and etc. Whereas with operation-based CRDT, the network have to provide certain guarantees for the delivery of these for these operations to the other replica, and that's kind of a problem, and that kind of makes designing of the systems a little bit harder, especially with like different clients, completely uncoordinated, working with the server. Also, server communication to the client has to be designed in a little bit different way. You have a question?
You mentioned that you've implemented lazy loading of data.
Yeah.
And were you referring to lazy transfer between server and client, or just like loading of data from business?
Yeah, exactly. So it's lazy transfer actually. So the trick is that we can just now disseminate the CRDT sets of metadata of the elements, and we don't need to transfer the data itself. And it's really beneficial because, of course, we can just have like on-demand loading of the data when user presses the button and says like, I do really want this type of data, then it will be reloaded separately from the server.
So is that content addressable storage? Like you have a hash and then it refers to the data?
Yeah. So actually, this metadata is kind of like a composite identifier of the data, which is optional in this case. So if you receive this metadata, you merged, you actually see that this data is not in your local storage, and then based on this composite metadata-based ID, you can ask the server, and server will always respond with that data. Okay, that's it. Thank you very much.